Hi everyone, my name is Valeriia and this is my presentation on my research I conducted on the solar flare evolution with my mentor, Diana Besa-Ionescu. Let's get started. I think that we should start with the definition of the solar flare. A solar flare is an intense, localized eruption of electromagnetic radiation in the sun's atmosphere. Flares occur in active regions of the sun and they affect all layers of the solar atmosphere. The plasma medium is heated to tens of millions of kelvins, while electrons, protons, and heavier ions are accelerated to the near speed of light. So in this video, you can actually observe the development of a solar flare. So here it is. Let's talk about the importance of flare research. As we know, the sun has a significant impact on the dynamics of our solar system. These explosive events result from the release of magnetic energy stored in the sun's atmosphere, manifesting as sudden bursts of intense radiation, high-energy particles, and also ejections of solar material. The impact of space weather and the potential to disrupt modern communications systems, satellites, power grids on Earth underscore the significance of understanding solar flares. So to understand these phenomena fully, scientists categorized solar flares based on their characteristics and spectral properties. The classification system employs an intricate network of criteria encompassing X-ray flux, duration, and spectral characteristics. In the picture, you can see four classifications of flares, where the weakest flares belong to class B, and the most powerful ones and the most brightest ones belong to class X. So to identify a flare, I selected the flare of class X 1.1 from the July 2nd. The data used in this project consists of images from the Atmospheric Imaging Assembly on board the Solar Dynamics Observatory, or SDO. This data is available online, credited to the Joint Science Operations Center, or GCOC. It's a collaborative effort by Stanford University and the SDO team. So I collected the images from all of the available wavelengths, so I could examine various layers of the solar atmosphere. And here are the wavelengths, and the A is for angstrom. It's a metric unit of length. So to analyze the images, I used free software called DS9 by encompassing the flaring area using a circular-shaped region. To represent the results, I created linear charts where x-axis referred to the time and y-axis referred to the surface brightness value. So my study utilized a dataset for solar flare over a specific period of time. On July 2nd, from 2330 to 2358, with the peak of X-ray flux at 2314. I divided all of the charts into three major groups. So let's start with gradual increase charts. Each of the chart of each wavelength has three vertical lines. Red one is for the start of the flare, yellow one is for the peak of the X-ray flux at 2314, and green one is for the end of the flare. So on charts of this group, we can see a smooth increase in the surface brightness, right? Which then leads to the peak of the surface brightness value almost at the same time, at 2318. So next group is sharp increase. Charts of sharp increase group represent fast and sharp increase in the surface brightness value to the peak. And the last group, charts with fluctuations. So on these charts, we see dynamic fluctuations in the surface brightness value. Another notable moment, each of the graphs experience early or delayed peak in comparison with other charts, which peaked almost at the same time, as I said earlier, at 2318. So before I end, I want to say that Talaria was one of the I don't know, best things I've ever done in my life. And the amount of new knowledge I got is invaluable. Also, I want to say a big thank you to my mentor, Diana, who was always there for me. Thank you.